Now we'll talk about solutions to equations. So when you have a coordinate plane, you can have a bunch of points on the coordinate plane or a bunch of ordered pairs that are just random. Or you could have some that form a line or some other type of equation. Equations can be linear, which means they form lines, or there are other special types of equations that you will study later. So here's an example where we have the ordered pair 3, 3, the ordered pair 1, 1.35, and the ordered pair -2, -1. These three ordered pairs all are on this one line. Now, all lines are made up of an infinite number of points or ordered pairs. You can think of the line as having so many points, so many infinite points, that they end up blurring into this one line. And so that's what the line really is. Now, the arrows, the end arrows on our line let us know that the line is infinite. And we also know that in between the points that I have shown here, in between these three ordered pairs, there are actually an infinite number of other ordered pairs. They may be a lot harder to find, especially since not all of them are going to land on whole numbers. You'll notice 1.35 ends up being an estimate of where this line intersects at this point here. So we can have ordered pairs that are not always whole numbers, and let's make sure you can read this one. So for 1.35, that means we went over 1 in the x direction and up slightly over 1 to about 1 1/3 in the y direction. All lines have a name, which is the equation for that line. And we'll see some examples of this. And then all the points or ordered pairs on that line make the equation a true statement when substituted into the equation. And we'll see some examples. So here we have -x plus y equals 2. This is the name of the red line that you see there. And there are a whole bunch of ordered pairs that I have labeled. So let's see if these actually are solutions to the equation -x plus y equals 2. So the first thing I'm going to do is substitute the ordered pair -2, 0. That's that point right there. So let's substitute -2 in the place of x. So that means we'd find the opposite of -2 plus y is 0. And see if that equals 2. Well, the opposite of -2 is 2 plus 0 does indeed equal 2. So we know that -2, 0 is indeed an ordered pair that is a solution to the equation -x plus y equals 2. Now let's see if -1, 1 is a solution to the equation. So I'm going to substitute -1 in the place of x and 1 in the place of y. The opposite of -1 is 1, and 1 plus 1 does indeed equal 2. Therefore, -1, 1 is indeed a solution to this equation, so it will be a point on that line. So now I'd like for you to try 0, 2 and try 1, 1.35. So first I substituted 0 and 2 in the place of -x and y. And there's no such thing as the opposite of 0, so we just end up with 0 plus 2, which is 2. So we end up with a true statement. Therefore, 0, 2 is a point on our line. Now, in the next example, we substitute 1 and 1.35. So the opposite of 1 is -1. 1.35 plus -1 just gives us 0.35. That is not equal to 2. So this is not a point on our line. As a matter of fact, we can see this visually. So here's 1.35 is approximately right there. So you can check this both visually as well as algebraically. The other 2 points we can just check visually. 1, 3 is clearly on this line, so it's a solution to the equation. If we were to check it algebraically, we'd get a true statement. And then 1 1/2, so we'd count over 1, 1 1/2 to about right there. You have to estimate when you're not using whole numbers, and then count up 3.5, 1, 2, 3, approximately 3.5 is right there. Why don't we do a check step with that one just to make sure we believe that that is a solution. So we have the opposite of x plus y equals 2. Why don't you do the algebra? Sure enough, when you substitute in 1.5 in the place of x, and you substitute 3.5 in the place of y, and you add 3.5 plus negative 1.5, you do get 2, which does equal 2. So try this problem by figuring out if A or B or both of those ordered pairs will make this a true statement. If they do make it a true statement, whichever ones do, then those are solutions. Remember, there are an infinite number of solutions on a line, right? A line has an infinite number of points on it. And the line is created when an x value and a y value are combined. No other line will have all the same x value, y value combinations. That's what makes the lines unique. And again, there are other types of graphs you'll study besides just linear equations, other types of equations that can be graphed besides linear equations. So you will not always graph lines. However, that's what we're focusing on right now. So go ahead and see which of these are solutions. You should have found that the second ordered pair is a solution to this equation, but the first one is not. Keep in mind there are an infinite number of ordered pairs. This is just one of the ordered pairs or points that would be on our line if we were to graph it. Try the two ordered pairs in this next problem and see which of these are solutions. You should have found the first ordered pair to be a solution, but not the second. Notice I am abbreviating solution with a shorthand, SOL''N. Try the next problem and see which one are solutions. In this problem, the first ordered pair is a solution to the equation. At this point, you don't have to show as many steps as I'm showing, as long as you're keeping up with the arithmetic, and you can just write yes or no. Try this next problem. In this example, neither of these ordered pairs is a solution. Now this is an equation that would not give you a line. It's not a linear equation. You'll learn about these types later, but it is an equation with two variables. Therefore, it has an infinite number of points made up of a combination of an x and a y value, or ordered pairs. So check and see if any of these points are going to be on the graph of this equation. In A, I did not have to do all my math to know that 2 is not going to equal 8 to the third power. And in B, I know that 2 cubed does equal 8, so that is a solution. Here I have the same equation, but different ordered pairs than the previous problem, so check and see which one of these. In this problem, the first ordered pair works, so you can tell pretty quickly the second one will not work. Again, in this equation, this is actually not an equation of a line, and you'll learn more about these special equations later, but go ahead and see if you can tell what ordered pairs would be on whatever graph this looks like. You should find that the second ordered pair is on is a solution to this equation, so whenever this was graphed, this point would be on the graph. Now give this one a try. In the first example here, the cubed root of 25 is not going to be a whole number because 25 is not a perfect cube, so it could not be 5. The square root of 25 would be 5. In the second example, the cubed root of 27 does equal 3 because 3 times 3 times 3 equals 27, so that is a solution. And remember, a solution is an ordered pair that makes the equation true when you plug it in, and there's an infinite number of these ordered pairs on the graph of whatever that equation looks like, because they're just all the points that run together to make a line or some other shape that you may study later.